Thank you. Hello. Good afternoon. I am Yasir Ahmed Idris, PhD candidate at Budapest University of Technology and Economics, and also I am a member at MRC 100 satellites. Today I will speak about the modern method for identification and tracking CubeSats based on resonant radar reflectors. We take MRC 100 satellite as a model. So my presentation outlines, I will talk about MRC 100 and the communication subsystems and the ground stations for MRC 100. Also, the concept about the resonant radar reflectors. Also, we had an experimental model to validate this method. Also, we had the results and the conclusion. Yesterday, my colleague Peter and Tibor, they spoke a lot of time of MRC 100, but I will highlight it in a few minutes. So MRC 100 is a 3BQ with dimension of 50 by 50 by 178 millimeters, with a maximum weight 578 gram mass. Sorry, there is a mistake. And overall power DC is 800 milliwatt, and the temperature range is -40 until +80 Celsius. Also, onboard MRC 100, besides the main subsystem, contains more than 13 scientific payloads. So, with invited passengers from local university in Hungary, like Győr and Debrecen and Szeged University. Also, all of the system here in MRC 100, it had code redundant buyer for every subsystems. So the communication subsystem. On board MRC 100, we had 3 types of antennas. The first one, it is about for the UHF communication for the telemetry and telecommand. And the second one is VHF quarter wave. And the third one is patchy antenna. This is for the S-band to transmit, to reach the 1 megabit per second. So for the communication subsystems, the uplink at 12.5 kHz and the downlink at 20 kHz for downlink. As we see here, we had a redundant pair for the subsystem, so for the communication subsystem. So the ground station, we had the main ground station for MRC 100. This is a 4.5 parabolic reflector type aperture antenna. This antenna had 21 dB in linear and 24 dB in circular gain. Also, the maximum transmit power is 1 kilowatt. Also, this ground station is fully automated, and we can control it through the internet. Also, can do all the post-processing of the received signal from the satellite. The secondary one, which is far from the primary one, about 20 kilometers, had gained about 16 dBi in isotropic. So the concept of the resonant radar reflector, the main idea of the resonant radar reflector is that, as we see here on the board, this is the communication subsystem. Here is the first communication subsystem, and this is the redundant pair of the communication subsystem. Here we can see this is a microcontroller for resonant radar reflector. So the idea is the usage of the VHF, UHF antenna of the communication subsystem as a reflector from RF illuminator from the ground. So this means there is no any RF radiation on board the satellite. So the microcontroller here is switched the pin diode here to form like +1 open loop and -1 short circuit. This is similar to be as BBSK modulated signal as a radar cross-section similar to the RF identification, but the distance between the tag and the reader reaches 3,000 kilometers. So this means the consuming power, it is about 3.5 milliampere. So if we calculate it, it is less than 10 milliwatt. So this means it is a few milliwatts. So the main concept is that this part, which is on the satellite segment, this is the reflector. This part on the ground. The first ground station, it sent continuous wave with 1 kilowatt RF power, and the reflector part is switches the pin diode to forming short circuit and open loop to reflect it as BBSK modulated signal. We received it by the second ground station, which is far from the primary ground station. It's about 20 kilometers. So, as we know that the satellite trajectory, the distance between the ground stations and the satellites, it is not fixed. The maximum, communication zero angle on horizon of the satellite is reached about 3,000 kilometers. Where the satellite is perpendicular with the ground station, the distance it reaches 600 kilometers. So, according to the two-line elements of the data of the satellite, we found that the satellite, it comes or cross Hungary every day, sometimes 3 times, and sometimes about 6 times. To operate this experiment here, to receive the backscatter signal of the satellite, BBSK modulated signal, we need that for every second, for every minute, we operate this type of experiment for 10 seconds, just 10 seconds. For one time the satellite, when we cross Hungary, this means it takes about 10 minutes. The overall time for the 10 minutes, it's about 100 seconds. For 3 times, this means 300 seconds. If the satellite came to cross Hungary 6 times, this means 600 seconds. The problem is that the integration time on the horizon, it needs about between 8,000 to 10,000 seconds. So this means we collect this data, we record this data, we need some days. So this is the eliminator part on the ground. When the ground station is sent about 1 kilowatt RF, this is the receiver part. The receiver part is coherent receiver with LNA and bandpass filter. So the type of the receiver is single sideband with analog to digital converter, and we record it through the sound card of the PC. So this is recorded as range and velocity matrices. The range is represent the time delay of the signal, and the velocity is represent the Doppler shift. So, as I mentioned before that, to record all this signal, we need about 8,000 seconds. So here we had experimental model. We do this experimental through our laboratory to validate this method. We use software-defined radio as transmitter and receiver, and here is the reflector part, and the distance between the illuminator, this part, and the tag is about 22 meters. And the receiver here, also the distance is 22 meters. The transmit power here, we use minus 43 dBm. This means it's about 9 watts. we found that, as we see here in the measurement results, here the waterfall diagram, this is of the reflected BBSK modulated signal, and this is the imaginary and real part of the reflected signal. And here we can see the spectrum of the reflected signal. It seems to be sin x over x. So the system can receive this type of reflected BBSK modulated signal. Here we can see the peak side loops of the back scattered BBSK code of the signal. So maybe it is not clear here, but it's about plus 68 dBm. So when we validate it and estimate it as a theoretical, we found that it is about, the big side loop, it's about 60 dB. So this means it makes sense, and the integration gain of the system, overall system, it is about 40 dB. So this means we can reconstruct, and we can receive the backscatter signal from the satellite. At the conclusion, as I mentioned before, the MRC100 contains two types of monopole antenna plus the patch antenna. Also, this system, we validate it on the VHF and UHF band, and we found that the integration gain, it is about 40 dB. Also, the integration time for these signals, it needs about 8,000 seconds to integrate all this type of backscatter signal. And also, the system validated as a laboratory, and according to the TLE data, we can reconstruct this type of backscattered BBSK modulated signal maybe in a few days. So after we validate this, this method from the real data from the satellite, we can improve it to detect the satellite on horizon and on the zenith region maybe in one day. Thank you. Joy.
So do we have any questions?
Thanks, guys. That's a great talk. So just to basically summarize, if I understand exactly what you did, so you send up a kilowatt constant wave, and then you modulate that on the satellite and receive that back down?
The basic aim is we send 1 kilowatt from the ground station to the satellite. The onboard antenna on VHF or UHF band can receive this data and this power, and the microcontroller inside the communication subsystem is switched periodically the pin diode to forming short circuit and open loop. So this backscattered to the ears looks like BBSK modulated signal.
Awesome. Cool. Yeah, no, that's amazing. And then I guess my question is, because you want to use this for tracking, do you need to know roughly where the satellite is initially so you can point that initial 1 kilowatt beam?
The main idea is not to tracking by position, but after we launch the satellite, we need several days to communicate with the ground station. During this time, we don't know the satellite is space debris is successfully launched. So the first step after we launch the satellite is the antenna deployment. We need to communicate or to detect this satellite by this method.
Okay, cool. Thanks.
Okay.
Any other questions?
Hi, thanks for the presentation. Do you have plans, the satellite is in space, do you have a timeline when do you want to try it?
Yes, during this December. We started to record it all, this backscattered signal, but the time it needs about, as I mentioned, 8,000 seconds. So we started 10 seconds every minute. So it needs recorder, and we build this RV matrices. After that, we can draw the tracking system.
So early next year we can expect results.
Yeah.
Quite good.
Okay. Thank you.